Hello everybody, I've got another physics video for us here today. Today we're going to be talking about magnets, current carrying loops, a little bit more about Lorentz force, all sorts of stuff. So let's jump right in. So I've got the first problem up here. You can pause and read it, but I'm going to point out some important things. The most important thing is that we have the magnetic field at the center of a circular loop, and this is a universal equation, so this would be great to put on like your equation sheet. And then if you've got a coil consisting of turns, you've got this equation for the magnetic field, with N being the number of turns in the coil. So up here with this first equation, you can imagine it's just one loop, and there's current going around the loop, and that creates a magnetic field in the center of the loop here. And then for the bottom one, you've got a whole bunch of coils stacked on top of each other. That's a really bad drawing of it, but if you can imagine, it would actually look more like this. And there's coils over here, the same amount. Yeah. More like that. So each of these are coils, and they're coiled kind of in like a compressed spring is what it looks like. And then there's still a magnetic field B in the middle of the loop. So the first question asks us, we've got an accelerator prototype. It uses a coil, so it's just one coil with radius of 0.15, 800 turns. Oh, I'm sorry, it has, it's not one loop, it's a lot of loops, 800 of them actually. And then a current of 5 amps. So we've got current, this is our N for our number of turns, and this is our R. So to compute the magnetic field strength, we want to use this second equation because we have, like I said, a coil with multiple turns. So let's plug things in. We've got beta, which is the magnetic field strength, equals N, which is 800, times mu naught, which is the permeability constant, that is 4 pi times 10 to the negative 7, times the current, which is 5 amps, divided by 2 times the radius. It's already in meters, so we don't need to convert. So we've got 0.15. I've already plugged this into the calculator, but if you plug it into the calculator yourself, you should get an answer of, depending on how you round, 0.0166 Teslas. So this is the magnetic field strength at the center of the coil. Second question is a more conceptual one. It asks us to analyze how the magnetic field changes if the current is doubled or if the radius is halved. So let's first see what happens if the current is doubled. So we've got beta equals N mu naught I over 2R. This becomes N mu naught I 2 mu naught I, or mu naught 2I, whatever you decide to write that as, over 2R. So you can see these 2's cancel out, and so it essentially doubles it, because you've got our original equation is N mu naught I over 2R, which could be written as N mu naught I over R times 1/2. And then by multiplying I by 2, we essentially get rid of the 1/2. So we're going to double beta. So to say that much more simply, you can say that if we have double the current, this leads to double the magnetic field strength. So now let's see what happens if we half the radius. So we've got beta equals N mu naught I over 2R. This becomes N mu naught I over 2, and then the radius is halved, so this becomes R over 2. So these cancel out. And we end up with actually the exact same thing, where in the first part of the equation, there's a 1/2 being multiplied by it. in the second part of the equation, there's that coefficient of 1/2 is missing. So we end up with the same thing where if you half the radius, you get double the magnetic field. Then the last question asks us to explain why a multi-turn coil provides a more effective magnetic field for beam steering compared to a single loop coil. And this is again just a conceptual question, and it can be explained simply by saying that beta, which is the magnetic field, is proportionate to N. So if you have a multi-turn coil, it's always going to have, you can't have a multi-turn coil with less than one N. If you like, you can even imagine this one up here as having an N, and this is just N is equal to 1. So beta, the magnetic field, is proportionate to N. So as N increases, beta increases. This is much more effective than, say, if you had a whole bunch of single loop coils lined up in a row, it would take up a lot more space than it would if you were to just have one smaller, more compressed multi-turn coil. So it's a more effective magnetic field than a single loop coil in that way. Okay, so this next question asks us about more about the Lorentz force, which is underlined here, and specifically the Lorentz force and how it relates to the centripetal force, how they're essentially the same thing. You can read this problem, but I'm going to go ahead and jump right into it. The first question asks us to derive the expression for the radius of a proton's circular motion as a function of, it looks like there's a comma there that shouldn't be, probably a function of time, using Newton's second law and the Lorentz force. So what this is really asking us is to set the two forces equal to each other and then solve for the radius. That might be a little confusing on when it asks us that there. But we have F equals QVB and F equals MV squared over R. So we can set those equal to each other. So QVB equals MV squared over R. Multiply both sides by R to get R so that it's not on the bottom. So we have RQVB equals MV squared. Then we can divide both sides by QVB. And we get that, you'll see that this velocity cancels with this one. So we end up with R equals MV over QB. And then it asks us to calculate the radius of curvature, so that R, for a proton. So we need the mass of a proton there, traveling at 3 times 10 to the 8 meters per second. So that's our velocity in an 8.3 Tesla magnetic field. And we know that this is a proton, so we also just use the charge of the proton. So the mass of a proton first, because we have R equals MV over QB, mass of a proton is 1.67 times 10 to the negative 27 kilograms. And then we have our velocity, which is 3 times 10 to the 8 meters per second. Then it's divided by the charge of the proton, which is 1.602 times 10 to the negative 19 coulombs. Finally, we have our magnetic field, which is just 8.3 Teslas. And then if you were to plug this into the calculator and calculate it out, you would get an answer of 0.377 meters, about, depending on how you round that. So it asks us to discuss how relativistic mass, so we're getting a little bit into the theory of relativity here, affects the accuracy of this result. Would the classical result over or underestimate the true radius? The answer is that it would underestimate the true radius, but to understand why, we need to look at question 4, which says that the LHC has an actual radius of approximately 4.3 kilometers. That is way, way smaller than our calculated radius. And the reason for this is found in the theory of relativity. I'm not going to get too deep into that. There's a lot of people who can explain that a lot better than me. But essentially, as a proton approaches the speed of light, all sorts of weird things happen. So while it may have a speed of 3 times 10 to the 8 meters per second, it doesn't actually have that mass of 1.67 times 10 to the negative 27 kilogram. It changes and has a more relativistic mass. So the answer is that this classical result severely underestimates the true radius of the LHC. Okay, so for our final question, we have a rectangular current-carrying loop that's placed inside the beamline to monitor the magnetic field. It's mounted on a pivot, free to rotate in response to torque. And then we're given the equation for torque on a current-carrying loop in a uniform magnetic field. I would definitely write that down on your equation sheets. And then we're given down here, we have the loop. It has dimensions 4 centimeters by 6 centimeters, carries a current of 2.5 amps, and then it's placed in a region where the magnetic field is 0.8 teslas and oriented at an angle of 30 degrees to the normal vector of the loop's plane. So the way that I'm going to solve this is I'm first going to draw it. It asks us to calculate the torque acting on the loop under these conditions. And while I don't really need to draw it because we have everything we need there, it is much easier to draw it and then understand it that way. So I'm going to draw kind of a perpendicular thing where we're looking at the current carrying loop. So here's our loop. It's rectangular. And this is looking at it from side on. So really, like behind it, it goes like this some more. And then it's hollow in the center. But I'm just going to look at it from side on view. And then it has a magnetic field. I'm going to draw that in red, oriented at an angle of 30 degrees to the normal vector of the loop's plane. So the normal vector of the plane is always just at a 90-degree perpendicular angle. So if it's 30 degrees to that plane, that means it's right here. And then this is our theta, which is 30 degrees. And so the magnetic field passes through this loop at all points, and the vectors are always at 30 degrees to the normal. Okay, so now we can see it, and it is a little more easy to understand. We already have our equation for torque. It is current times the area of the loop, which is in meters squared, so we will have to convert to meters, times the magnetic field strength times the sine of theta. So let's first convert everything to meters. So we have 4 centimeters by 6 centimeters. So we can do 0.04 times 0.06 as our meters. And this is, I cannot recommend enough converting to meters before you do everything. Because let's say you do 4 centimeters times 6 centimeters, you're going to end up with, that's 24 centimeters squared. And then you're going to have to convert from centimeters squared to meters squared. Whereas if you convert in the first place, you've got 0.04 meters times 0.06 meters. Let me calculate that real quick. 0.04 times 0.06. You end up with 0.0024 meters squared. And you may think, it's a common mistake. We had 24 centimeters squared earlier. And so people like to think, well, I have 24 centimeters, so I can just move the decimal 2 places to the right. But you see, that gives us a different answer. Because this centimeters is squared and we want it in meters squared, we actually have to move it 4 places to the right. But to avoid doing that entirely, I say always just convert to meters right at the beginning and your life will be much easier. Okay, so now we have our area in meters squared. So we have torque equals the current, which is 2.5 amps, times the area in meters squared, which is 0.0024, times the magnetic field, which is 0.8 Teslas. And then finally times sine of 30, because that is our theta. So if you calculate this out with the calculator, you find that we end up with 0.0024 Newton meters as the answer. And then it asks us what orientation of the loop relative to the magnetic field would maximize the torque. So we look at the equation for torque and we think, okay, what changes with orientation? Well, the current isn't going to change, the area of the loop isn't going to change, the magnetic field itself isn't going to change. The only thing that's going to change is theta. So since we want the maximum torque, we want the maximum value of sine of theta. And this happens at 90 degrees. So the orientation of the loop relative to the magnetic field that maximizes the torque is at 90 degrees to the normal when it aligns perfectly with the magnetic field. You can imagine this is here, here's our current carrying loop, here is the normal, and then we have our magnetic field would be pointing this way, and this would create that 90-degree angle. And this creates the maximum torque because it's going to, remember that the current carrying loop is free to rotate in response to torque. And so it is going to cause it to rotate until it is perfectly, it's parallel. The normal vector and the magnetic field vector are parallel with one another so that there's no torque. And that is it for this physics video. Good luck as always.